So, how are you guys? So this is the last actually presentation before the lunchtime. So, I think we will be like quick enough to not be late at the lunchtime. So my name is Georgy Okrokvertskhov. My short name or nickname is Gosha, which is much easier. And we have Alex Shaposhnikov as well. And so here is the agenda for today. So we will just walk through what we are doing, who we are, so what is our test setup. And then we will explain what we have as a result and what we were able to achieve in our labs, and then do a quick summary. So what we should expect from Kubernetes at scale, especially when we are running applications and not just running some artificial or synthetic tests. So who we are? Actually, we are members of performance teams, which is a team of 12 engineers at Mirantis. So Mirantis is a company who was primarily focused on OpenStack, but a year ago we started actually looking into other technologies, specifically into containers. And Kubernetes was one of the interesting applications which we started to use. And the first work with Kubernetes was actually related to running Kubernetes on top of OpenStack. So that was our first experience with Kubernetes. And we were mostly focused on OpenStack, and we are doing a lot of stuff in OpenStack community. So for example, we have performance working group who is focused on the testing of OpenStack scale and performance. And we plan to extend this activity onto Kubernetes and containers as well. So we are working closely in a partnership with Intel, and Intel actually provided us a physical infrastructure for running those tests. So all this scale testing requires a lot of hardware, and this is pretty expensive exercise. So thanks Intel, we have two different data centers. So one is rented at Rackspace, where we have dedicated physical 250 nodes. And we have Intel data center, where we have 500 node lab. So Alex can walk you through the hardware, so what we have in this lab. And as you remember, so this is Intel hardware and Intel lab.
So yeah, our lab based mostly on the Dell R630 servers, which are 2 sockets, have almost top-notch Xeon 5 CPUs, which are 12 cores, physical ones, so it's 12 virtual ones, have 1/4 terabyte of RAM, 2 800 SSDs, and which is quite more important, one of the latest Intel X710 NICs, which are kind of giving us a hard time to figure out the best combination of the operation systems or kernel, NIC drivers, and they are pretty not in beta, but they are still not always stable, and optimization, which we offloading and stuff around them, which we playing, turning on, turning off, and working on the performance. So another lab consists of the Lenovas, which are also having top-notch CPUs, press the same one, set up the same NICs, and well, it's pretty the same one. So here's how our networking looks like. So we have a leaf-spine technology used between the racks, and we're using L3 and BGP. So this is specified VXLAN overlay that for future, for doing some other stuff for different networking solutions vendors. But right now, we're using Calico. So we have 35 racks. That is the biggest one lab, so we're talking about 500 nodes. And so that we have, each and every server have 2 dual head NICs. So each and every server have 4 10G ports, which are connected to different switches. Switches between themselves have MLAG, and that aggregated on the spine switches routers. We have BGP populated everywhere. Kind of, I already mentioned fixed LANs, but fixed LANs right now not used on the switches. Let's switch to the next slide.
Right, so another important part of performance and scale testing is to be able to reproduce all those tests. And for that, we had to create automation, and we heavily rely on the automation in this lab. And the most actually painful part is to do automatic provisioning, because we have to start from bare metal. So we have automation which automatically provision all those like bare metal nodes in different configurations, and we can dynamically split those 500 nodes for like different smaller environments if we need to run multiple different tests or do some experimental work before we run this at a larger scale. And for provisioning, for bare metal part, we use heavily Cobbler. We recently started to play with Ubuntu MAS, which came with Ubuntu 16. So that's the version which we use. And for Kubernetes provisioning, so once we have operational system, and it's usually Ubuntu 16.04, long-term support version. So for Kubernetes provisioning, together with Calico, we use Cargo, which is one of the related projects in Kubernetes ecosystem. So once we have our environment deployed, we have like Jenkins, which used for running specific tasks, and then we run all those test suites which we have, and all the results will be collected in several databases. So we have Postgre databases just like store some aggregated statistics, but for time series we use InfluxDB. And once we have all this data, we have special tools which will do some analysis. So we use R language to do some statistical research. And all those results are automatically published and generate like RST documents, which we can then upload to the internet almost automatically. So this system also used in OpenStack, and that was a community standard at those time when we started all those activities. And what we are looking for is to extending this approach for Kubernetes community as well. So just like high-level understanding what we have in more like graphical format, so like Jenkins system, which does all like jobs, and components which I mentioned, like Cobbler, Postgres, and InfluxDB. So when we deploy Kubernetes, we actually rely on the reference architecture, which is implemented in Cargo installer. And Cargo deploys highly available Kubernetes configuration. So we have 3 nodes which are running etcd cluster, and on the same nodes we are running Kubernetes masters. So we have like API services running there. We have like Kubernetes scheduler. And Cargo itself uses Hyperkube distribution of Kubernetes. So the recent versions, specifically what we used in our lab, are mentioned here on the slides. And then we have like minions nodes, and based on the specific environments, it could be like from 20 to 500 physical nodes. We also use virtual machines, so we can create virtual environments when we spawn like up to 4 or 10 VMs per physical node, and then we use them as a minions. So that's another option. So when we need to test a large number of Kubernetes minions, and we do not have enough like physical hardware for that, we switch to the virtual machines. So testing approach. So we have two tools which we're heavily using. So we have OpenStack Rally project. So this is a tool which was specifically designed to test OpenStack API. So OpenStack project was all about like APIs, and we have a tool which allows you to create pretty complex scenarios and like execute various API commands and collect different API-related statistics. But it looks like that when you heavily rely on API, it does not necessarily represent the actual state of the running applications. So the next step, like beyond API testing, is to be able to deploy a special application which allow you to collect application-specific metrics. So, for example, we have a tool which runs so-called like master or collector, which sits on top of MySQL database. And then we run a lot of pods, and in each pod we run container which has a simple agent which just reports back to the collector service, I'm up and running, and here's my timestamp when I send this message. So based on this tool, we can actually figure out what actual was going on top of Kubernetes cluster. And actually, it will show pretty interesting results further on. So just like briefly what we usually measure. So we can measure API response time. And there are several blogs on kubernetes.io related to Kubernetes performance. And they test almost usually Kubernetes API response times. But also with our like collector tool, we measure the actual time of response from specific containers, and we can actually figure out is there a difference or there is no difference between those like API responses about pod readiness and actual running application readiness. So as our title says, so we are running this for specific application. So during the last year, we made a pretty big effort on moving OpenStack from bare metal to the microservice application, which can be hosted on top of some platform-like system, like Kubernetes, or like container management system like Kubernetes. So OpenStack itself was created as a service-oriented architecture application, which actually allows us to move it from bare metal and standard deployment approach to microservices model. So there are still some stateful components in OpenStack. It's mostly related to storage and databases, which OpenStack uses. But overall, so each API component of OpenStack is like stateless application. And we almost have one-to-one mapping between service in Kubernetes and OpenStack service. So far, we achieved this configuration. So we took like most frequently used OpenStack services and containerized them. And we have like 19 Kubernetes services which represent OpenStack components. And each service uses replica sets. And as we use self-orchestrating microservice approach, we rely on config maps so that each component of this application, when it starts and running, it will be able to find its own configuration, and it will be able to discover other components. which it depends on. So we can achieve this with this configuration. So in the details, it looks like that. So this is a specific OpenStack service, which is called OpenStack Keystone. And this is like identity management system for the OpenStack. And as you see, we have like deployment, which will create a service. Service relies on the ReplicaSet, and each OpenStack Keystone instance will be running as a pod. And this allows us not only to easily deploy OpenStack, but also it allows us to do like day two operations. So if we need to upgrade OpenStack service, we just like produce a new image for the Keystone service, and then we ask Kubernetes to do rolling upgrade. And as this service is stateless, it's pretty straightforward to use Kubernetes rolling upgrades to perform service upgrade for the OpenStack. So as OpenStack API should be like externally available, we use ingress or external load balancers to distribute like incoming external traffic among the like pods. So you can see how it looks like from the Kubernetes perspective. And when we go to the big picture, so that's the application like OpenStack, which is a massive application. And this is how it looks like when it's deployed at large scale. So we have 3 nodes with Kubernetes master, and we never deploy any other like applications on top of master nodes. So Kubernetes have those physical nodes like dedicated to Kubernetes components. We also say that, okay, let's all OpenStack services deploy on their own dedicated nodes, just because each OpenStack service actually generates pretty huge loads on the node. So it uses a lot of like CPU and memory. So it's better to physically figure out what will be the placement rules, and we use like node selectors to specify which like deployment topology we will use. And on each Kubernetes minion, we run exactly one instance of OpenStack Compute, because this OpenStack Compute component will manage libvirt and KVM hypervisor on top of this physical machine. So we need to have exactly one instance of OpenStack Compute on each physical node, because that's the process which will manage underlying hypervisor on the operational system level. Very good. So let's go to the interesting part, results. So Alex is an original author of this collector system. So that's the results which we collected by this tool. So Alex, if you can walk through what we did.
Yeah, okay. So here's the dependency of the ReplicaSet creation time versus ReplicaSet size. So as you could probably see, it's almost invisible when there is a kind of ReplicaSet size. It's only one ReplicaSet, I need to mention that. So if ReplicaSet size is 100 pods, so it's kind of quite fast. 500 pods, also kind of pretty quite fast. So it's kind of, the time is seconds. For the 1,000, 2,000, 5,000, 10,000, as you could probably see, it's pretty linear. So scheduling of the pods in terms of one ReplicaSet is pretty linear. And it's pretty fun thing to take a look on the percentile. It's kind of, if you properly see that, this percentile is kind of pretty interesting. It's kind of quite like it should be. So which is kind of very, very unusual. So Gosha probably will try to explain what's happening.
Yeah, so before that, let me setback as well. So those results are pretty consistent with what you may see on the Kubernetes.io research. So, and that's pretty much one-to-one mapping between the test type. So on Kubernetes blogs, they were running like 10 replica sets, and they were like measuring time of replica set deployment versus number of pods. So we replicated this scenario, and we pretty much confirmed that the linear dependency between replica size and deployment time is like our confirmed in our experiments on physical nodes. So in this test, we were running Kubernetes on physical hardware. So this is like 500 nodes Kubernetes cluster. It's not a virtual machine. And the interesting difference, as Alex mentioned, we have in percentiles. So this 50 percentile is not exactly the median of this big 99 percentile bar. And that's pretty interesting effect when you start looking into details and start looking into dynamics, so how those pods were created. And with our like collector tool, we have an ability to figure out which pod reported at what time. So you will see some nice plateaus, and by accident or not, but those plateaus specifically related to number of 500, which is our number of physical nodes or number of minions. I don't know, is there any relation in scheduling, but that's the like actual natural experiment which we did, and we saw those dependencies. So the reason why like 50 percentile is not exactly the median of the 99 percentile bar, just because of those plateaus. So as you see, we were trying to create 1,000 nodes, 1,000 pods, and at 500 pods, scheduling was stopped almost for 10 seconds, and then it started working again, and then it stopped again for specific amount of seconds, and then it's like proceed. It looks like there is something in scheduling which actually creates those gaps. And we will see those effects on other tests. But when we say linear, yes, it's linear when you have a like bigger scale. So when you run like 10,000 nodes, all those gaps will stay like closer and closer. So at bigger scale, you will see a nice like line with some small like deviations from the linear law. But at smaller scale, those effects are pretty noticeable. And when we go to the bigger scale, so that's our another experiment where we were performing rolling upgrades. So on initial phase, we deployed a ReplicaSet with 500 pods. And then we created a new image, uploaded to registry, and then we asked Kubernetes to perform rolling upgrades. And as a result of parameters like update periods and polling intervals, we have this nice straight line which actually says that this rolling upgrades works as like linear algorithm. One by one, it was like recreating those pods. There is no any like anomaly seen in this process. And as you see, when we like increase the scale, all those problems with steps are not noticeable.
So I'd like to a few words about it. So we exactly mention it, what the parameters we used, because the default ones is a little bit different. So update period will be 3 seconds, and the poll interval, as far as I remember, is 1 second. So because of the poll interval is kind of slightly increased by default, upgrades will be happens a little bit kind of slower. So that parameters will allow you to put all these updates, I mean, in probably somewhere around 20 minutes. So for 500 size of the replica set. But if you go with default ones, it would be kind of bigger, maybe 5, maybe 10 times. So it's these 2 parameters, because the polling, it will, as far as I see, that container is up and running, then a new pod is up and running, it decides to go and upgrade another one. So that parameter is very, very important if you plan to do that faster. It depends on use cases. So.
Yep. Okay, so the next step for us was to figure out if there any difference if we use nodeSelector, because from like our intuition, we were like thinking that probably this will somehow affect the process of scheduling. And as our application heavily relies on the nodeSelector, that was pretty important for us. So we ran those tests, and actually within like the error of measurements, there is no difference. So there are still some like plateaus during the scheduling process, but from like time perspective, there is no any effect of the using of nodeSelector on the scheduling process. But when we go to more complex scenarios, which you might see actually in applications. So here we have multiple replica sets with 100 pods in each one. And those replica sets were actually defined in a single YAML file. So this is a single kubectl command to create this configuration. And we were expecting that those replica sets will be created more or less in parallel mode, but that's actually not the case. So it's not a parallel process. So initially, it looks like a sequential process. So the first replica set was created, then the next one started. So there is a little bit overlap. So it's not exactly one by another, but this overlap is pretty small, and the time gap between replica set creation time is actually significant. So another interesting effect, which we can see on this picture, is grouping. So it looks like that there is some scheduling algorithm or some like processing algorithm in Kubernetes, which actually process several or few replica sets at once. So we see grouping like 3 or 4 replica sets which are created almost simultaneously, or at least almost together. But between groups, there is still gaps in time. And this actually may lead to potential effects when you use a lot of replica sets in your application. So in our case, when we have 19 replica sets which we create simultaneously for OpenStack, we actually expect that it will be created simultaneously, and then our components will figure out their like dependency and orchestrate themselves through the etcd, which we use to figure out who is already configured, so where is the location, so on and so forth. And it should take some specific amounts of time. But what we see in the results is quite interesting. So because of this grouping effect, which is not actually deterministic, so we don't know which replica sets will be like grouping together. So we have an interesting problem, and which actually creates an effect of prolonged deployment. So within first minutes, like specific, almost random sets were created. And so all those components have actually dependencies on the services like RabbitMQ, which is used as a message bus between all those components. So all those services which were created on first minutes, they were waiting for the availability of the RabbitMQ service and components, which were created only on third minute. Just like because of this grouping effect and because it's not actually created in parallel mode. So in ideal situation, and that's what we expected initially, that when we create all those replica sets, at least one pod will be created almost simultaneously. Then we will have processes running. Services will actually detect this replica set in a health situation. And all this like self-orchestration will happen. But actually, as a result of those delays in the replica set creation, all the orchestration started almost at the like fourth minute when all those replica controllers were created. So that actually might be interesting effect on the application deployment. And this was caused by this scheduling mechanism or like a replication set mechanism. Right, we're almost there. So.
Yep. So for the networking, that's pretty expectable results. So we just did a few tests for the figure out how to basically just to mention that we're using Calico right now with the Kubernetes. So for the networking, it looks like kind of you almost get the wire speed with kind of pretty small MTU, so standard MTU 1500. And it's kind of limited by kind of, you see speed of 2 links because kind of using only 2 links in this 4 links bonding, so we're using kind of 2 bonds from out of that. And it's kind of, if we try to use 4, we have to go and maintain the different pods. So create basically just multi-threaded load between the different pods. So we tried that, we see the expectable results, so it would be about 36 gigabits. It's kind of close to wire speed, so usually kind of 90% is fine. So let's go to the summary.
Yes, so summary is like based on what we saw, but still you need to remember that statistics might actually show different results and may have like different interpretations. But first of all, when you look onto basic like performance tests, like we have published on Kubernetes.io that says, okay, we can easily create like 1,000 of pods in Kubernetes. That's all true, except so there are other like effects which are not covered by those tests, and you cannot actually rely solely on those tests to predict the time of deployment of your application. So as you saw, there are some other effects based on the replica set numbers or any other like object numbers which Kubernetes might have, and your projections might not be very accurate. So from networking side, we didn't see much effects, but there are different, there are some. Specifically, we saw problems with service discovery. So when we were running large amounts of workloads which generated traffic, obviously kube DNS subsystem was overloaded, and we saw like delay in the Kubernetes service discovery. Scheduling is linear, but still, as usual, there are other effects which you need to take into account when you plan your application deployment. And because of like replica set behaviors, when you create your self-orchestrating application, you might need to take into account those effects. Right. And there were a few issues which we mentioned when we were running those tests, and those tests were running on the bare metal. So first of all, Docker running in production might be tricky. So we saw multiple instances of problems when Docker process was hanging. So, and the typical symptoms, you see your like Kubernetes pods in status pending or like creating, but nothing actually happens. And then you like log into the system to Docker PS, and it just like hangs. And the only solution for that is to restart Docker process, which might affect your running or already not running containers on this node. And Kubernetes itself does not handle this situation very well. So it just like waits, and there is no like communication between Docker and Kubernetes, but Kubernetes will never reschedule such pods. And that might be a huge problem at large scale when you have like production environment. So when you use Calico or any other networking solutions, troubleshooting is a nightmare. So they use a lot of like underlying technologies, BGP, IP tables, and other stuff. And it's without like proper tools, it's almost impossible to properly like trace your networking stuff. Especially when like developers create their containers, they is trying to reduce the image size, so they remove all like networking tools. Like yesterday, we were trying to troubleshoot one of those problems, and we had no like ping commands in the container, so we were unable to do anything. So that might be a big problem. So don't forget about like troubleshooting tools, because it might save you a lot of time. And Kubernetes itself is not very good with diagnosis and collecting all those like problematic areas. So we saw several instances of problems when TNS were not updated and Kubernetes were unable to do anything. Or we saw an instance when Kubernetes node was actually like Kubernetes minion was not reporting back to the Kubernetes master, and Kubernetes was unable to remove pods from this minion, and we were trying to remove this namespace, and this never happened because like termination process was waiting for those pods, and Kubernetes was unable to do anything. And it's hard to diagnose those problems, so it will require a lot of efforts before you figure out what's the root cause. So the last part, like as we were engaged with Intel stuff, so I have to put like legal notice about like performance results and their dependency on the hardware. So it's right there. So here's the links. So here's a tool. It's publicly available on the GitHub. You can use it. So, and we have a lot of Kubernetes and OpenStack related stuff on the OpenStack performance documentation page. So you're welcome to go and see what we have there. So there are interesting like comparisons of Kubernetes, OpenStack components, like bare metal provisioning system. So it's not specifically related to OpenStack. Okay, that's it. Thank you. Any questions?
I had a quick question on not so much the
we end up with creating PXE server, like with Cobbler, which bootstrap all those machines via EPMI interface with a small initial image, and then inside this image we are running torrent-based system, which actually pulls the actual operational system image, and this actually allows us to distribute the networking traffic.
That is my real question, which is, it sounded like you're bandwidth limited where you make
Yes.
parts. Why did you use like bonding or add more NICs to?
Because we were limited to specific like hardware configuration which we had.
Yeah, so for torrent distribution kind of allows us to basically distribute traffic between the nodes, as soon as the node downloads the image, it's starting to distribute it. So.
Question. Did you have the container images already running on the node, or did Docker have to download them?
So when we run tests, we actually run the initial like warming route, which downloads all the images to the minions, and then we rerun those tests. So it's pure time of Kubernetes and Docker startup. So it's not specifically like bound to the image pool. Yeah. So we.
Just to follow up, did you use a load balancer or maybe a virtual IP solution in front of your multi-master solution so that the minions are talking to multiple masters?
I don't think so, at least
No,
not
right
in
now,
this
no.
deployment.
It's not tuned
Yes.
this way, but as far as I know, it's in the roadmap.
We use load balancer in front of registry, obviously. Yes, but not in front of Kubernetes. So we have pretty like powerful hardware. So at 500 node, we didn't see any problems with running Kubernetes master on a node and so like redirecting all the traffic to this node. It's a powerful machine. It's like 12 cores and a lot of memory. So Kubernetes is pretty capable to handle all this load.
I think the only thing that we'll be kind of thinking about that we have a limited resource on and the scheduling. So there is no, as far as I know, there is only development going on the multi-scheduling in Kubernetes, so we kind of are waiting for it because it should change the situation dramatically for us.
Mm-hmm.
So you're using Rally for part of the testing.
Yes.
Testing suite. But then you also mentioned that you have like, catching and diagnosing problems in Kubernetes in general. Do you think there's any? Do you think some work could be done to like Rally can help?
Rally might help, but it's not specifically a diagnostic tool, right? So there should be a set of tools, probably as a part of Kubernetes distribution, which are specific to Kubernetes problems, right? As well as for networking. So if you run like things in production for troubleshooting, you probably like have to have a special image which you can like quickly start a container with, and this image will have all like necessary tools for networking troubleshooting. Because like in typical situation, in standard containers, there is nothing, and you actually can't do anything.
That's even
Yes.
for the Kubernetes itself. I mean, like if you're using service, so you're using HA, kind of not HA, but load balancing using IP tables for that, with some kind of chance of sending some particular kind of session to some particular server. And it's kind of like we playing with 1,000 nodes. Some of them are populated with sometimes with 1,000 services at the same time. So we have 1,000 records of the IP tables for the service itself. And with a lot of probabilities, they are different ones. And it's kind of, if one of these services are not working, and if the IP tables decided to schedule on him to this particular kind of basically translate this particular request, this particular session to the service, you will never know about that because next one will go to the next one. And that is kind of, well, very, very hard to figure out what's going on because the toolkit which was written, it was written without kind of this not just kind of trying to figure out how it works, but it's written in a way that it will fail on any unpredictable thing if something is wrong. So in this case, one of the DNS services just sometimes is lax. Tools written, using producer consumer way, so it's kind of, it aggregates the request and put them to the MySQL to decrease the cost of doing that and increase the responsiveness. So in this case, there is each and every consumer will try to create connection to MySQL. So it will be, on our case, it's 96 consumers because of the twice of the number of virtual CPUs, and one of them will fail. Which one? Those is just go and exit. So I mean, in case of the application we will done in this particular rate, we'll just die and we will never know what's going on.
Any questions?
Why is the best did you do faster the communication, the latency between the different containers? Every command you test the computer node to the master node, but not the
No, so the test was actually between between minions. So the traffic was flowing between minions. So there is no any workload which is scheduled on the Kubernetes master. And we specifically placed those containers on the nodes which are in different racks, because then it will flow through the spine instead of like being bounded by the top of the rack switch. We did, so first of all, obviously it's not like very extensive test, so it's just like basic one. So we didn't see a huge amount of problems, but when we were running multiple containers, so we saw uneven distribution of the throughput between containers. So you might see the situation when overall you have 18 gigabits per second, but one container will have like only 30 megabits, and another one will have like 4 gigabits, and another one like 1 gigabit. So that's more advanced scenarios and requires a lot of like specific testing for the networking. But
So
yes, we
also
saw
kind of-
those problems.
Because you go into the container world, you usually assume that you must power even kind of much more containers because of the little overhead, much more than VMs. But in this particular case, that each of them could create, each and every application will create a different footprint on the networking. So we probably have to come up with some QoS stuff, networking things, on the networking provider for the Kubernetes. So in Calico, there is no such thing. And there is have to, I don't know actually kind of solution which kind of fully implements all requirements which are kind of very, very will be useful in container-based kind of deployments.
Okay, cool. Thank you guys. Thank you for coming. That's lunchtime, so let's not miss our lunch.
Thank you guys.